guys, welcome in this new video. In this video, we will be discussing some further topics from our previous video of graph-based algorithms and graph data structure. So, in the previous video, as we discussed about the introduction to graph, traversals, back edges, cycles, SCCs, and topological sorting, we will be just continuing some further topics in this as well in this video. And if you haven't checked that video, then do check it out from the I button at the top right corner of this video. So with no further delay, let's get started. So we will be discussing like what is a minimum spanning tree and what are minimum product spanning tree and some algorithms that can be used to find these minimum spanning trees. Okay, so with no further delay, let's get to the first algorithm of Kruskal's minimum spanning tree algorithm. But first we have to actually know what is a minimum spanning tree. So a minimum spanning tree is basically a spanning tree in an connected and undirected graph that is actually used to connect all the vertices of the graph with minimum weight possible. Okay, so a spanning tree of a graph can be multiple, but a minimum spanning tree of a graph is the minimum weighted spanning tree that if their weights are summed, then it will give us the minimum weight possible from other spanning trees. Okay, so we have three algorithms, like one is Kruskal's algorithm, one is Prim's algorithm, and the other is Boruvka's algorithm. So first we will see the Kruskal's minimum spanning tree algorithm. So in this, what we do is that we just arrange all the weights of the graph edges in an ascending order and just connect one by one in an ascending order, so from the minimum weight to the largest weight. Okay, so like in this you can see that we have just sorted all the edges according to their weights, and now we will just connect all the edges with from the minimum weight to the maximum weight possible. But we have to consider and keep in mind that we do not run into a loop kind of thing that can be lead to a cycle in graph. So you can see this diagram that first we connected one, then two, and like these we get a minimum weighted spanning tree. And in exam you basically use this algorithm to do the fast calculation, because any algorithm that uses this like which is used to find the minimum spanning tree will lead to only one minimum spanning tree in the graph. So it doesn't matter in exam that which algorithm you use, but yeah, if you have to do the fastest way, then use the Kruskal's minimum spanning tree algorithm. Now coming to Prim's minimum spanning tree algorithm. So in this, basically what we do is we just select a vertex, and then what we do is we connect all the nearest edges which are having minimum weight. So let's say if you connect like you start from 0, then you will connect 4 from this edge to 1 which is having 4 weight, then you will just connect from 1 to 2 which is having 8 weight, then we will connect 2 to 8 from this 2 weight. Like this we can go on and just have two sets where one is the minimum spanning set of the given graph and other is the unvisited nodes in the graph. Like this we can actually find the minimum spanning tree as well. And this is somewhat a bigger algorithm, so I recommend to use Kruskal's in the exam, but we should also know this algorithm as well. Now coming to the Boruvka's algorithm. So in this, basically what we do is we just have each vertex as a component, and then what we will do is we will connect the nearest two vertices with an edge that is having the minimum weight. Okay, so let's say first we will just have each component for each vertex. Then what we'll do is we will connect these components with the minimum edge. Like let's say if we want to connect 2 and 8, we will be having 2 as the minimum one, then 6 and 7 can be connected through 1 and 6, like this. And every vertex should have connected with some other component with a minimum weight. Okay, and at last we will just be having like these three components in manner that will be having minimum weight, and then we will be just connecting them with some other one edge that will be having minimum weight. So like this, Boruvka's algorithm is also a greedy type of algorithm, just like Prim's algorithm, and it also yields us the minimum spanning tree. So now coming to the Steiner tree problem. Basically, Steiner tree problem is just a kind of a minimum spanning tree as well. In this, basically, minimum spanning tree is a broader term for the Steiner tree, because this Steiner tree, in the Steiner tree, what we are given is we are given a graph and a subset of vertices in the graph. So basically, let's say if you are having this graph and you are given a subset of this graph, let's say containing 0, 1, 2, 8, and 7 vertices, then you need to find the minimum spanning tree on in this particular subset only. So basically, if you have a minimum spanning tree in this particular subset of the graph, then you just tell that this is a Steiner tree, okay, and the given set of vertices in that subset is actually called the terminal vertices, and the other vertices that are used to construct the Steiner tree are called Steiner vertices. Okay, so the Steiner tree problem is to find the minimum cost Steiner tree. So as I told you, and you can see this example as well, in which we are given a graph and we need to find the minimum Steiner tree of this graph. So basically, it is kind of a minimum spanning tree only for this particular graph. Okay, but as we are given that we have to use A and D as the terminal vertices, so we will be having this 2 and 10 as the subset. Okay, because as we are given A and D as the terminal vertices, so we need to just construct a tree that will connect these terminal vertices with the minimum edge weight possible. Okay, so this will be our minimum Steiner tree for this graph. Now let's say what is the basic difference between a spanning tree and a Steiner tree. So a minimum spanning tree is a minimum weight tree that spans through all vertices, and if the subset that is given to us, or the terminal vertices, is equal to set of all vertices in the Steiner tree problem, then the problem becomes a minimum spanning tree problem. Okay, and if the given subset contains only two vertices, then it is just a shortest path problem between those two vertices. Okay, and one more important thing is that minimum spanning tree is a polynomial time solvable problem, but a minimum Steiner tree problem is an NP hard problem, and the related discussion problem is NP complete. Okay, so the application of Steiner tree is to minimize the cost of connection among various important locations in the VLSI design, that is the very large scale integration of the ICs and in computer networks as well, and other applications are also there. Now in this Steiner tree we just use an approximate algorithm because it is not a polynomial time solvable problem. Okay, so now coming to the minimum product spanning tree. So basically this is similar to the minimum spanning tree. The difference is that in the minimum spanning tree we used to add the weights of the spanning trees which are possible in a given graph, and we find the minimum of them. But in the minimum product spanning tree we will just multiply those weights in the different spanning trees, and we will use the minimum product of the weights in the spanning tree to be the minimum product spanning tree. So in this we can use Kruskal's and Prim's algorithm as well, but Kruskal's and Prim's algorithm use the summation. So what we can do is we can actually convert the weights in the graph to the logarithm weights, so that when we add them, then it behaves like a product. So just like in this diagram, we converted the logarithm, these weights, to the logarithmic weights, and we can now apply the Prim's and Kruskal's algorithm to find the minimum product spanning tree, like in this. So this was it for today, guys, and I hope you could understand these important topics. So till the next video, keep learning and keep watching.